So the stage is yours.
Well, thank you very much for this kind invitation. And it's a pity that I cannot be with you really live, and I have to do this virtually. Yeah, so I will be being the outlier of this in this lecture series, because I will mainly talk about applications of AI and machine learning, but I think this is also okay. Just to note, this bifold that was also mentioned, it's hiring, talented people can and should come to Berlin, and hopefully the pandemic will be over soon, so then we can also not only enjoy sitting in our home offices, but also meeting again. Okay, so then that's the plan for today. I will talk a bit about explainable AI, and also about applications, and you can immediately see how these things come together easily. So if something is burningly urgent in terms of asking questions, then put it into the chat, and I will not monitor the chat very closely, so somebody flag me this somehow. Anyway, so let me just come to this first part, which is about explainable AI. And the reason that people started looking at this was that everybody complained that machine learning methods, they're just a black box, and you can't know what's happening, and you can't know what the machine does and why it does something. And so with all these complaints that I found here very reasonable, at some point, for example, myself, but many other people started to devote a lot of research to this. My first paper on this goes back to 2010. We have been making some progress, and you will see that. So here's the scenario. So if we want to explain what a machine learning method does, the scenario that I'm looking at is the following, where you have on one side, I hope you see my mouse, on one side you have a model that is fully trained. It could be a deep neural network, it could be a kernel machine, it could be something. And now transformer, LSTM, whatever, right? And so the question is, assuming that this model is now trained in computer vision, because then you can make, show nice pictures. Why, for example, does this model think that this picture is the picture of a rooster? And clearly, this model has been trained very well, and so it has learned what the rooster is, and so it will possibly and probably predict that this is a rooster if it's a good model. But the question is why? And there's a fundamental problem in this, because this beast here is a very nonlinear mathematical function. So in a way, if we want to go back from a decision to the input, we have to go backwards through a nonlinearity, which is, of course, a mathematical challenge. So this was essentially unsolved until we came about with some first solution that was the so-called layers-wise relevance propagation algorithm, which allows us to go backwards through the model and to attribute to each input variable, in this case these are pixels, the probability with which this pixel is relevant to this model. So just to make this clear, this neural network model has been trained on some training data. This is now a test data point. The network predicts out of sample. And the question is, why is this out of sample prediction? Why is it thinking it's so roosterish? And here's the heat map that should explain that. And you can see that basically these red points here in the image, they're very hot. So this means that they are very relevant for the decision-making process. Green is totally neutral, and blue would speak against roosters. So you can see it's the rooster's comb that is the most relevant feature that this model has considered. And of course, if you think about it, being able to understand what a model does in the decision-making process is important. Now, of course, if you think about computer vision, maybe you could do without, because you know, nobody dies if you get the rooster wrong or for the wrong reason. But if you think about medical image analysis, it looks different. So let me just explain this a bit more. There's different ways, approaches to explanation. Maybe the most popular one, and that's also one that, you know, in engineering, sensitivity analysis really goes back, you know, to the early days of control theory, where you look at, you know, the gradient of a function, and then you see how much sensitive a function is with respect to a single variable. So the question, hello, yes? Can you say the question?
Some echo from the audience, so yeah, you can carry on.
Okay, good. Okay, so sensitivity asks the question which pixels lead to an increase or decrease of a prediction score when they are changed. So because the pixels in this case were the input variables. In other words, the question is what makes this image to be classified more or less a car, a horse, a rooster. So the explanation that LRP, for example, from the last slide does, layer-wise relevance propagation, and other algorithm do is wants to decompose the function into contributions of the pixels, and in that sense, which pixel contributes how much to the classification. In other words, what makes this image to be classified a car or a rooster or something. The third approach and question is we would like to match a single input pattern for some classified object class in the light of the learned model. So all of these questions and approaches, they ask really fundamentally different questions. And so I would like to urge you to really think about what is the question that you really want to answer in an application when you want to explain stuff. Quite often it would be the explanation approach, but sometimes you also want to know about the whole class and the whole ensemble of data. Then it would be the deconvolution. So sensitivity is sometimes, in the control setting may also make sense. So it's really different for different applications. So here's a shameless self-advertisement of a book that we wrote. It was the first book on explainable AI. And here's now an explanation of how LRP works. So in a deep neural network, you have the input, you have some weights, and then you do a forward pass through the model, and there's some nonlinearities on the way. So in the end, you read off what the output units tell you, and here the the largest activity is for ladybug, because this is a ladybug and this model has been classifying well these different animals. But the question is, how do you give these explanations? In this case, the model is staying fixed, so none of the weights are changed, and you would like to go from the output towards the input along this graph. So what you would like to do is you would like to take, as a first step, you would take the output activities and you call them relevances. And then, in the next, in order to compute the relevances for the layer below, you compute a sum over all the upper layer relevances according to the weights that you have in your model, and you normalize it and you multiply it with the forward pass activity of that unit. And you do that now for the next layer and the next layer, the next layer, until you have the input. So looking at this formula, this is one possible update rule for explanations. Looking at this formula, you wonder, is this just a hack, or is there some mathematical reason behind it? And there is. This was the first algorithm where we could have some theoretical proof that this was doing, in a sense, something optimal. And so that's called the D-Taylor decomposition. So there's one ingredient that we still need, and that's the so-called relevance conservation property, which means that if you do this game of going backwards through the model, you should avoid that these relevances explode when you go from layer to layer. So you need to make sure that the relevance from between all these layers, they are conserved. So that's also part of the algorithm. Okay, so if you have that, then you can explain all sorts of models. You can explain neural networks, you can explain kernel methods, LSTMs, transformers, whatnot. And so, for example, this model classifies this coffee as coffee. And the reason for it is because of the crema. Or, this kernel model thinks this is a cat, and it's because of the fluffy part or the mustache. And of course, cats, they come in different shapes and backgrounds, and so you can see that depending on the very situation, the model considers different aspects more cattish than others. So then let me see the relevance conservation is actually something that is, so to say, included in the way the computations in the relevance propagation work. So it doesn't need to be included in the network. The network is the network, and you don't have to fiddle with that. That stays constant. But the computation along the graph considers the relevance property. Okay, so let's digest a bit. So here's some example. So you have an image. This image is classified as a scooter image, and you have the sensitivity and the LRP, and you put this next to each other, and you can see that LRP provides the answer to why is this a scooter, and that's basically the front tires, the back lights, the wheels, and whatnot. And sensitivity asks, what if I change one pixel, does it become more or less a scooter? So this part is interesting. So this is basically street. There's no scooter here, but of course, if you change some pixels on the street, then you may change them such that they become scooters. So that's what the sensitivity analysis gives some large response here. But perhaps it's not what you would like to, to know for this kind of task. So I guess most of us may prefer the LRP solution. There's one further thing, which is this LRP can say some positive and negative things. So give positive evidence, for example, classifying this as a class 3, which the model does. You can see it's a 3 because there's now a stroke here, or because there's something here. And you could also say, what's the evidence for class 9? Of course, it's not classified as class 9, but you can still ask that. And you can see that this is 9-ish and this one too. But the fact that this is not closed speaks against the 9. So this is kind of a nice thing, because you can query your model, if you wish, about the classes that classifies, and also the classes that are not classified, maybe the second best or the worst. And you can understand what the model thinks about this. Okay, so then let's just come to one aspect which I find interesting. I've always been teaching my class that machine learning models, they focus on the generalization error. So this is really the most important thing. So we have some data, we train our model, and we would like the model to be good not only at the data in our hands, but also at the unseen data that is out there. And so basically, we would like to have a model that generalizes well. Okay, and I think everybody would say, well, the generalization error is really what we need, because that's the standard thing in machine learning. But is it telling the whole story? That's the question that I'm now asking. And I'm giving you an example which will allude that this is not the whole story. So here's a computer vision exercise where you have some benchmark. The idea is that you need to distinguish between all these different classes, and you have some models, and in this case it's Fisher, which is a popular model, and some deep net. And typically in your paper, your computer vision paper, you would have a great deep new model, and it would beat everybody on this task or on some other task, and you report the generalization error in the table. That's all you report, by the way. And for example, here in some classes like horses, both models are almost on par. I mean, this is not statistically significant as a difference, but Fisher sucks for dogs, but then chairs, it's basically the same thing again. And so you can compare how good the models are, and both of them are more or less state of the art. So now you can, of course, given what I taught you about the explanation, you can actually try to see how the models actually solve these problems, and what their strategy is. And this is what we do here in this image. So here's an image of a horse. Obviously, both models say that this is a horse, so both models are right, correctly predicting this out of sample horse image. Now you can ask, with layer-wise relevance propagation or some other explanation techniques, so what's so horse-ish about it for the model? And here you can see it's the horse's nose, it's the rider, it's the horse's butt, and that's it. So it's the object, which is good because that's what you expect. And on the other side, Fisher is a bit more interesting, I would say, because it's also a bit of the horse's nose, it's also a bit of the horse's butt, but most, reason for classifying this as a horse is really the lower left corner. And that is kind of peculiar because I don't see a horse in this. Now, if you look very closely to the picture, then you can see that there is a copyright. It says Lothar Lenz, Pferdefotoarchiv.de. So when I showed this to my wife, and I said, this model is no good, right? It's cheating. Then she said, well, no, this horse, this model can read. Therefore, this model actually focuses on the copyright tag, and it's kind of because it's not a stupid thing to focus on a copyright tag that is in the horse class, but it's something that is not. This has nothing to do with horse pictures in general. It has to do with the data set. The data set consists of many thousand images, and nobody really looks at them. So it happens that in this particular class, there's a copyright tag, but this has been gone mainly unnoticed. So this means that if you look at these two models, then, on one side, the deep neural network looks at the object, and on the other side, the Fisher model looks at some artifact. So this is quite a difference in strategy. And if you think about, this not being an innocent horse that is to be classified, but some really serious medical imaging task where you diagnose some patient, then it's clear that you would rather like to have this type of model and not this one. And you can't see it from the generalization error. So the conclusion from that is that we need to analyze our models well. We need to understand what they're doing. And let me just go one step further, another horse. This horse is his name is Hans. It was a horse in 19-something, early 1900, and this horse was really a media sensation because allegedly this horse could do math. So this person, the horse's owner, would show on the board some addition exercise. So you add 3 and 5, and then the answer is of course 8, and the horse would then use its foot and tap on the wood 8 times, and so the horse would always get these math exercises right, and so it was quite a sensation, and of course the media went crazy about it, and this was around the planet until some word of reason came into play, and people came to the conclusion that unfortunately horses cannot do math, and it's really rather horses are extremely sensitive to reading their masters, and basically the horse was trying to read the human, and they could even exchange this horse's master with some other human, and still the horse could get the math result right. So the media now called the horse Clever Hans because the horse was able to solve the task, but for the wrong reason, not by doing math, but by paying attention to something else. And so this is the reason why we coined the expression Clever Hans strategy, which is, this model solves the problem for the right reason, and this model also solves the problem, but for the wrong reason. So it's using a Clever Hans strategy, making use of the copyright tag. And we have been trying to look at that at scale, trying to see, can we find these Clever Hans strategies of models, because there's a lot of models out there that people are using that, you know, have great generalization errors, but very strange artifactual strategies of solving the problem. So here's the idea. So there would be a model, and the model is trained very well on, and so it generalizes very well. And now you would like to understand what the strategies of the model is. And one way is, of course, to look at all the heat maps of the million data points out there, but this doesn't help very much. You wouldn't like to do that. Instead, you would take the test data and run it through your model, have the classification, and go backwards and get all these heat maps. And then what you would like to do is you'd like to, after proper normalization, you would like to cluster them. So we use spectral clustering, and then we can see how many clusters are reasonable for that. And you know, just we cluster them by measuring the similarities between these heat map images. Okay, so and you know, we can see that we get 4 clusters in this case. And then we can start analyzing these clusters, and then we can take some prototypes from these clusters and look at them, and then try to understand, you know, what the strategies have been that the model is using, you know, for the data from these respective clusters. So which means that we only have to look at 3 or 4 at each cluster, but not at a million data points. And so here you can see these are the more obvious clusters here, these 2. It's basically portrait and landscape pictures. And then you have the copyright here, and always the model is using the copyright tag for the classification. So these are basically the copyright tag models. Then this one is also an interesting one. You look at the horses, and you can see, you know, the most important thing for the model was not the horse itself, but rather, you know, the bars, you know, with the of the riding exercise. So it's not it's rather the context. And then finally, these pictures, this class or cluster, you have the right heat maps at the place where the horse is. So you can see these different strategies. Now, people have complained, of course, about this and said, well, you know, you've used a much too simple model, and, you know, this is not going to happen for one of the state-of-the-art models and whatnot. And you know, you have used the particular explanation methods and so on and so forth. But you can also do this for and also we have used the Pascal VOC data set, and there's much larger data sets these days. And so we basically scaled this up and also took some ImageNet data and the most state-of-the-art ImageNet models. And again, we did this exercise, and here's for the airplane class, we have some interesting finding. So this is also 2 strategies recognizing airplanes. And this one here, the green one, is a bit peculiar. So if you look at the heat maps, then the heat maps are really a frame around the picture. Now the airplane is in the middle. So why would you know, have a frame around the airplane? There's just sky there. And so it turned out that the culprit for this was that, you know, when collecting these large data sets, it's really that people have different sizes of image, and they use so-called cropping in order to rescale them to the right size, which means that you put some randomness outside. But the way the randomness was done is quite telling for this airplane class. So it's what we actually recognize is that the cropping algorithm for pictures that contain a lot of sky, airplane pictures, that this is totally telling about this class. So the cropping has been used in the same manner for 30 years, the computer vision community. But if you think about it again, then you can change the cropping to be a bit more sensible to the statistics and a bit less telling to the airplane class. And then, you redo the whole thing, and then this frame goes away and the classification rates for airplanes go up. So which means that your understanding of the data set and the models has given you rise to actually better models afterwards. Okay, so this was gaining insights about your neural network models or your data set, but there may be also insights that you could get about strategies about the sciences and so on and so forth, and I will focus on that now. There's a very interesting work that was done by the DeepMind folks, and they have studied a number of arcade games, and we tried to so we used these models that they came up with and analyzed them with layer-wise relevance propagation. And I'm now looking at the arcade game called Breakout. Here, by the way, on the left side is sensitivity, so this you don't see much, but on the right hand is LRP, and you can see that after a while of training, the models are very good, and the models understand what is important in a certain situation for the game. So the ball is important, and the paddle was important in the very first beginning. And now that there's a tunnel, it's only up here that anything else doesn't matter to the game engine or to the neural network. But now it's again the ball. So now the ball has almost no meaning. It's all just the upper part. And so you can see that, in this case, the model that was provided by these DeepMind folks has beautifully learned a game strategy of an arcade game just from looking at pictures and being trained in the way this arcade game challenge is set up. So there's other arcade games that we also analyzed, which is, for example, the pinball game. And if we analyze that, then it's clearly of clever Hans nature what was found as a solution by the deep neural network model. In particular, what the deep neural network model does, it moves, it nudges the table until the ball hits a switch, and then it moves it up and down the switch until high score is reached. So basically, there's no activity at the paddles. So of course, in the real world, nudging the table, it can only be done to a certain extent, and until there's tilt. But what the neural network model has learned is that nudging the table is quite possible in this setup that of the arcade game being used there. So it's a bit of a cheating, but it's an intelligent cheating. But it's not doing anything that would resemble playing pinball. Okay, so we'll come to some very serious stuff, which is machine learning, the sciences, and I will talk a bit about quantum chemistry because I've been very interested in this field for a long time. And so these are the folks that have been doing this together with me, and there are many more. So I just to explain a bit, I don't know whether any of you have heard about IPAM. It's the Institute for Pure and Applied Mathematics. So the Brits have their Newton Institute, and the people in the US, they have the Institute for Pure and Applied Mathematics. The good thing about the IPAM is that it's at UCLA, meaning Los Angeles. So the weather is fantastic always. But after this advertisement of IPAM, I should say something about the program. This IPAM also has long-term programs. And the nice thing about these long-term programs is, as in the Newton Institute, is that there's a number of professors coming together and a number of PhD students and postdocs, few enough so that they actually really interact with each other. And then they stay together for 3 months, and there's a bit of a workshop program and so on and so forth. So when I was invited to one of these meetings, this was 2011, I had a sabbatical coming up, and I thought, well, that's a good idea. Let's go to California. And then I'm a machine learner, and when we had our tutorial week, everybody around me was talking about quantum chemistry and about DFT. And of course, I knew that DFT was not the DFT that I was used to. The density, they talked about density functional theory. I know DFT as discrete Fourier transform, but they were all talking about quantum mechanics. But in my life, I graduated in theoretical physics, so in my master's, and so I did strings and things like that. So I'm a trained quantum mechanician. So it came back. It started to come back, and so the idea of what they were interested in was really this very innocent looking equation. So it's the Schrödinger equation. It governs the properties of matter, in particular the quantum mechanical properties. So it looks like a very innocent eigenvalue equation, but if you would naively try to solve it, this would be like a 10 to the 60 dimensional inversion problem, which is nonsensical. You wouldn't solve it that way. But what people have been doing, because you cannot, you can only approximately solve the Schrödinger equation, is to have different approximations to study that. And one being that density functional theory, which also got Nobel Prizes. And so that, takes the nuclear charges and the positions of atoms of a molecule or material and does some computation to get the quantum mechanical properties like energy, band gaps, and all sorts of things. This typically takes a couple of hours per molecule, or of the order several months for a material. So most of these quantum chemists and the climate people, they are the culprits for these huge supercomputers and their use. So what I suggested then was to say, instead of actually doing this approximation to the Schrödinger equation, why not just take a machine learning approach to all of this? So how about taking some of the data points that you get from these DFT calculations and trying to train a machine learning model, and perhaps the machine learning model can predict the outcome of the Schrödinger equation well, which was kind of, when I suggested this, didn't go down well for most people, because mathematicians tend to like to solve their equations and not predict their outcome, and physicists didn't like this idea, but chemists, they were quite neutral to this, because whatever solves their problems solves their problems. So the good thing about this was that you could really predict very well the outcome of the Schrödinger equation with any kind of machine learning methods, including neural nets. And so there's this vision that we have developed, which is that we all know that physicists have been charting space, and by charting space, we know something about our universe. But there's really a universe of chemical compounds. Even the small chemical for small chemical compounds, because there's such a combinatorial manifold of them. There's more small chemical compounds than atoms of this universe. So the chemical compound space is really vast. And so trying to map or chart this space is totally unfeasible with the standard DFT type of approaches because of this extraordinary computing times. But machine learning methods, they get us closer to being able to chart things, at least selectively, because a machine learning model would make the right prediction within fractions of a millisecond. And with that, we can start charting the space. We can start getting a feeling for this. And so since we started this in 2011, there's now a large community and several IPAM programs, one running at this very moment. And they have been, we've been understanding chemistry from quite a different perspective now and contributing to that field. So one interesting point is if we now use, say, a neural network to do that, and this is now a very short version of a very complex neural network, which can predict this out of sample prediction of quantum chemical properties at something like 0.3 kcal per mole, where already 1 kcal per mole makes chemists happy because that's chemical accuracy. So this is a complex model. It's called the deep tensor neural network, but there's also a convolutive neural network version, and so on and so forth. Now, the question that we ask ourselves is, can we explain what this model actually does? Can we understand what kind of chemistry does it learn? Is there any insight about how the chemical environment of an atom is represented by the model in the light of the data it sees? And so we could also try, now we don't have heat maps, but we can color a molecule, we call them gummy bear plots, and we can pretend that we are, for example, an hydrogen atom, and look at the benzene, and we can see what is the, in quotes, chemical potential that this neural network would implement about the benzene. And we can do this for different atoms, we can even take groups, and so that gives us chemical insight. There's even some insight that we could get from that wasn't there in the data before. So this is where it was really a first moment when we could train a machine learning model and we could gain understanding from the finished trained model. Okay, so let me just go one step quicker, and then we conclude and you can ask questions. So one other approach, which is in medicine, was to train machine learning model to get insight about cancer. And here the typical thing is that we have some slices that cancer biologists or pathologists look at, and these are huge slices, like easily 100,000 pixels times 200,000. So we make some smaller pictures from that, and for each picture we ask the medical professional whether this is cancer or not, and then we train a neural network or machine learning model to do this classification. Now, since we have this explanation method, we can understand what the neural network model has learned, and we can understand how this reflects to the pathological picture. And so here, for example, would be the heat map for this particular case, but I will show you a bigger one. So here would be the pathological slice, and this would be the heat map, and this would be the overlay. And you can see that in this particular cancer type, we would look more to the cell bodies, but there are also ones where you cancers where you would look more to the stroma and so on and so forth. So that's kind of an interesting thing, because you can now take some histological data, but you could also classify into cancer, non-cancer, or stroma, or lymphocytes, or something. And for all of these classifications, from the images, you would get a heat map of why the model thinks that this is cancer or lymphocytes or stroma. But you can decide not to stop there. You can also go and say, well, how about taking the pathological slices and predicting molecular marker profile, so molecular expressions, for example. And there's one molecular expression for whole slice, but the model tries to predict this, but still there's a spatial resolution that it gives back. And for most of these, perhaps 60,000 different molecular profiles, they cannot be classified. They're random because they have nothing to do with the cancer that we're looking at. But perhaps for 50 or 60 or 70, there are some things that we can predict, and then we can look at these heat maps, and then we can have, put things together and provide images which can, try to give us some insight on the carcinoma, on the tumor infiltrating lymphocytes, but also on the molecular properties, and we can overlay this and try to see whether we can get new hypotheses about cancer, because the explanation in this case tells us something that the model has learned, and this could be nonsense, but it could also be something interesting. And so, because we looked at this very carefully, we got the impression that it's very interesting and not at all nonsensical. And when we submitted our paper, the referees, they said, well, you're a bunch of machine learners, of course, with some pathologists also on the paper, but we don't believe this. So we actually did some experiments where we took the particular morphologies, and we made a prediction to some particular molecular markers and their expression, their spatial expression. And then we also did the respective staining. And so you could see this is the staining. This is basically the ground truth, but it's the slice after this one. So it's not exactly the same slice. It's just one slice. It's, you typically take 6 or 7 slices, and that's the next one. So you can see that this is the prediction that the heat map gives, and this is the prediction that the heat map gives for another case. So you can see that what we are actually providing, and that's ecadarin, which is notorious for a particular cancer. So we can see that what we are inferring gives us new insight that we can validate, but also we can now use this and do all sorts of statistics and gain some novel understanding. And I will now come to a conclusion. So I tried to explain explanation, explainable AI, and try to point out why explaining nonlinear models is essential, why it's not really enough to only look at the generalization ability. It's this kind of research is quite orthogonal to improving deep neural networks, but it can be used and has been used to also improve the neural network models. So we believe that there's need for opening the black box because it's totally unsafe to use neural network models out there that use Klepper-Hans strategies. So there's a new theory, which is the basis of layer-wise relevance propagation. This method is providing a basis for gaining insight. And the gaining insight is really quite interesting because we can gain new insight from the chemistry side or new insight from the medical side, or at least provide some hypotheses that allow us to guide our experimentation. So with that, I would like to stop and to ask for questions.
Thank you very much, Klaus. So yes, for questions, is there any question from the physical audience? Yes.
Okay, thank you very much. So when we have a neural network and we train it, we always like this neural network to be regular. So we, in the loss functional, we put maybe the L2 norm of the parameters, and this ensures some regularity of this forward map. But then if we look at the backward map, which gives the important parts in the features, is there a way to regularize this backward map, like by adding some penalization term in the functional?
Well, so I think your question allows me to reiterate what I have been saying before. So what I've been talking about was more, I mean, the layer-wise relevance propagation and other methods are methods that are post-training. They are applied post-training. So you don't change the model after that. So you train your model as good as you can, and then you try to understand it. And you may actually understand something, and then you perhaps find some oddities in the training set, and you remove them and you retrain your model, or something like that. So what you're asking is, whether there can be some kind of regularization in the training of the neural network model, which is of course another thing. That's also an interesting thing, but this is not what I've been talking about, right? And perhaps you could, you would maybe if you would like to ask another question, why would you want to do this regularization? In what sense would you want to regularize?
Yeah, because maybe you want some kind of, if you input different outputs, but similar ones, you want the neural network to be looking at the same parts of the input. Like, I don't know, if you look at only at one corner and then you change it a bit and then you're looking at completely different things, then, I mean,
but
would be a problem.
I would say if you want to have some kind of invariance, then you would do, you would include it in the training in the first place. And when you're done with everything, then you can analyze your model in the way I explained it.
Okay, so it's always an analysis that is done a posteriori.
So that's what I was talking in this talk, right? And there's also, of course, different lines of research where people also would, I mean, for example, we had a paper where we say, how about using what we know from explanation to prune a neural network, to make, to cut some weights. And that works very well. But this is always going towards a particular question, right?
Yeah. Okay. Thank you.
Other questions?
Are there other questions from the physical or virtual audience? I see there is possibly one for the virtual audience. Okay, so I believe that slides will be available soon. And another question, could you please explain why does the transfer learning work and what are the mathematical conditions that allow you to apply it?
Maybe I'm not understanding this question very well. I haven't particularly talked about transfer learning. So maybe you can type some more explanation, because I think transfer learning is something great, where you try to learn something from one domain and transfer it to another domain. And of course, for any of these models, you can later on use explanation methods to understand, what has been transferred and so on and so forth. So we've been doing something like that in the context of neuroscience, of classifying fMRI data. But perhaps can you be more specific?
Yeah, if Natalia, you want to type some more details about your questions. Meanwhile, if there is some further question,
hello.
Oh, okay. Hello.
Actually, easier to say me than to type. Actually, I have met one mathematical paper where the authors said that, okay, we will first train the model, like it was a machine learning model for solving a PDE, and they said, okay, we will train a model to train this particular PDE, and then when we meet another PDE of this class, but with completely different parameters, then we will apply transfer learning, and everything will work very quickly and great. And then there was no explanation behind it, and I kind of have seen in the internet that, like, for example, people train a neural network to recognize, let's say, dogs, and then they remove one layer, and then they kind of use this pre-trained neural network to recognize, let's say, birds, and it works. But in this mathematical context, it caused some confusion. So the question is, what should be like the mathematical foundation for people to apply it, or it's just
okay, now I understand the background. So let me just say something which is more general, and I can't help you with the math paper because I think it's not fair to say anything if you haven't read that one. But I can speculate a bit about it. So the reason why transfer learning works is, or pre-training, as you rightly put it, is that you you have a large data set, and the neural network tries to solve some tasks, say a classification task, dogs, whatever, and then you think that this neural network has in its hidden layer a representation that allows to represent images well. And so there's some features, and people often make the analogy to the brain, where in our human brain, in the visual cortex, the in V1, V2, V3, and so on. So you actually have some extracted some features, some low features like edges or end stops, but also some higher order features. And these have been learned, so to say, by the neural network, some features that represent images in general well, and then you use that and fine tune for a novel task. So that's the idea, and the condition under which this works is a bit common sense. So if you would say take images that come from natural images, then taking all of a sudden some images that are not natural images that come from a totally different distribution, maybe this approach wouldn't work so well. So it needs to come from a similar ballpark. So in some sense, if you wish, the neural network has provided some function space, and in this function space, things can be expanded very well. If you now think about the PDE, the question is whether there's some function space in the PDE world that is universal to several PDEs, or to at least a class of PDEs. Perhaps that's what they do.
Thank you.
And is it possible to look at this in the lens of information theory, i.e. information content relating to the pixels and this flows through the network? Yeah, that's a very good question. So yes, one can look at this, and there's I was using LRP because that's our method, but there's a zoo of other methods out there. This is now a larger community with hundreds of people working there. And there's also information theoretical or game theoretical approaches, like Shapley value would be the game theoretical approaches. So, okay, does heat map work well to catch small pixels? Yeah, okay, this is a good question. So I think it's not a question of the heat map, whether they catch small pixels, but rather of the trained neural network. So if you think about a neural network, a convolutive neural network that has a hugely too large convolution filter, then it will miss some small details. So if the model is able to get the small details, then typically the heat maps will also do. I mean, you could see that in the pathology case. These cells are very small and very detailed. They are not all looking the same, and still you get the fine details, right? Other questions?
Any further questions? I don't see any in the chat. No. So I think we can thank you again.
Very good. Thank you. Thank all of you. And it was a pleasure. And have a very nice further meeting, and enjoy the lectures. Okay, then.
Thank you. Thank you very much, Klaus.
Thank you.